Let me give you a little bit of an idea of how this test works and what it actually looks at. Remember that the purpose of a chi-square test is to compare proportions in several groups. Alright, so we're going to compare groups. For the sake of illustration, let's say that we have 3 such groups. Doesn't have to be 3, it could be 2, sometimes even 1, or 4 or 5 or whatever. In most situations, however, you're not going to see a large number of groups. And we're going to compare these groups according to a nominal variable. Again, for the sake of simplicity, I'm going to assume that it's a dichotomous yes-no variable, although it doesn't have to be that way. It could be a nominal variable with several values. Now, what we're going to do is we're going to say, all right, let's assume that we're going to test a number of cases, a number of subjects, let's say 300, just because we have 3 groups. And so let's say, again, for the sake of illustration, that we're going to test 100 subjects in each group. Again, those numbers don't need to be the same. I'm just using equal numbers just to clarify the concept, but those sample sizes can be different. Now, what we're going to do is we're going to look, after we have done the experiment, we're going to look at the total responses. So let's say that in this case, we ended up with 120 yeses and 180 nos. Okay? Now, what do we expect to see for each group separately? Well, under the null hypothesis, remember, what would the null hypothesis be in this case? Well, it would be that the proportions are going to be the same in all of the groups, right? The null hypothesis always tells us things are the same. So I would expect in each of the 3 groups to see the same proportion of yeses and nos that I saw in the totals, and that would be 40 and 60. So I would expect in the first group to have 40% or 46s, and for the yeses, and 60 no's, and the same in the second group and in the third group. Okay, so this is what I would expect under ideal conditions under the null hypothesis. Right? Now we're going to see what did we actually observe. Let's say that this is what we observed. Now you can pause and have a look at those numbers, and you'll notice that those numbers are not exactly the same as what we expected, but they're fairly close. It is entirely possible that these variations, these slightly different numbers, occur just because of chance variation, random variation. So in that case, the p-value will be fairly large, and we would end up saying, yeah, we don't have any evidence to say that the 3 groups are any different. However, let's say that the observed values are these ones. Now you'll notice that even though the no's are still in the majority in each of the 3 groups, but the 3 groups are divided between yeses and no's quite differently. The first group is predominantly no's, while the second and third group are almost 50-50. Okay? So in this case, it starts to become a little bit hard to say that the 3 groups have the same proportions, right? So in this case, the p-value may end up being small, and therefore we may end up rejecting the null hypothesis and concluding that yes, there is a difference. Okay, so how do statisticians do that? What they do is, again, they compare the expected frequencies to the observed frequencies. And for those of you who are mathematically minded, they do that according to this formula, which is called the chi-squared formula. Squared because it involves certain quantities squared, and chi, well, just because they picked the Greek letter chi. Okay? So notice again that when those differences are large, then the chi-square number is going to be large, and so that will mean that, oh, we saw something quite different from what we expected. So probably the p-value is going to be low, and we may end up rejecting the null hypothesis. If, on the other hand, those differences are going to be small, then the chi-squared number is going to be small, and that will lead to a large p-value. And that's basically the idea. You want to go through it again if you want to, but don't worry too much about that. Let's look at, instead at some important points to consider about the chi-square tests. Okay? First of all, the chi-squared statistic measures how different the observed data are from the expected. So once again, the values of this chi-squared statistic are often reported. You're often going to see them in an article, but they're rather useless to us, the users of the article. Okay? Those numbers don't really tell us very much. In fact, the only thing that they tell us is that the chi-square test was used in that particular situation. So that's okay, but probably that piece of information is somewhere else. So if you look at a table which has maybe a column of chi-squared values and you're scratching your head trying to figure out what they mean, just move on. They do have a meaning, of course. They do have content, but it's not a content that is useful from a clinical applied point of view. The second thing to remember is that the computation of the p-value, so how we go from the chi-square statistic to the p-value, they actually use some kind of an approximation. I'm not going to go into the theory of that, but they use some kind of an approximation. And that approximation actually only works well if the sample sizes are fairly large and if, in fact, the expected frequencies are fairly large. And that is why we had that requirement for this test for the expected frequencies to be large. So when we look at that contingency table that we saw earlier, in each one of those cells, the expected frequencies, the actual numbers, the numbers that we actually saw, should be fairly large. Okay. Also, in order to accommodate for some special situations or sometimes for the lack of some of the requirements, there are some other variants of this test that go under different names, even though their basic principle is still the same. So we're going to look at some of those variants and see what they're called and what when they are used.